Before we go any further into the other standard collections, these new ones like list and set that we haven't seen before, there's one more thing that I want to introduce using vectors, just so that we feel comfortable in the setting. It's another abstraction, and it's an important one. It's one that we haven't really needed so far for two different reasons. One of them is that vectors already have indexing, which we can use to work around this issue. But the other one is that we sort of have been working around this problem all along. So many of the problems we've been solving with vectors so far haven't needed this feature. And that might be sort of the result of a bias, not necessarily that vectors are any more flexible than some other collection. So what we need is to explore what it means to hold our place at some point in a collection. So, for example, as we iterate over a vector, if we use indices, we could keep track of what index we're at as a way of sort of holding our place at a specific element of the collection. If I want to, for example, find where in the collection the element 10 occurs, I could make a note of index 2. As a way of knowing where in the collection I go to find that thing. And indices are a sort of natural way of doing that for a vector. The problem is, I often want to hold my place while iterating over lots of things. So as an example of why I might want to do that, here I have a for each loop that iterates over a vector. And we know because of the way for each loops work, we just get every element, and then in this case, we print it out. But we also occasionally write loops that don't go over the entire vector. They sort of stop halfway through. They iterate halfway through a vector and then stop. We might even write loops that iterate halfway through a vector, then stop, and then later another loop picks up the remainder and iterates through the rest of the vector. And we can do that by, for example, keeping an index variable and just using the same index variable for both loops. But the question is, if we want to do something more complicated than just using a for each loop to iterate over a collection, if we want to hold our place at a specific place in a collection, what do we do for collections that are more exotic than vectors? And more generally, if we are using this idea of collection as an abstraction, so a bunch of elements that we're keeping somewhere, is it really a good idea? Should we really be worrying about things like indices, which are sort of a vector-specific feature? And the answer is, well, we do need a way of holding our place in whatever collection we're working with. So we may not always want to write a loop that loops over the whole collection at once. And also, of course, we shouldn't assume we're always going to have indexing, because as we've seen, lists and sets don't. So there is a general feature we can use, and it looks a little bit horrifying at first. And all I can say by way of condolences, I guess, is that at least we didn't have to cover it in week 1. C++ has evolved a lot over the past decade. One of the biggest things, I think, the biggest improvements made around 2011 or so, is that we no longer need this feature. It's a feature called an iterator. We no longer need this feature until we get to this point in this course. Previously, before C++ 11, we didn't actually have for each loops. And that meant if you wanted to loop over a collection more exotic than a vector, you'd have to use this feature all along. And trust me, you can't, once you see what we're going to talk about in this video, you'll agree that although you can digest it, you really would rather not have seen this a couple of weeks ago. So what I want is an abstraction for the idea of holding my place at a specific element in a collection. So some general way, some generic way that I can keep track of a specific position inside a collection. And the way we're going to define this will seem a little bit odd for vectors because indices are so natural. But keep in mind, we're doing it this way because we're eventually going to want to hold our place in collections that aren't vectors. And so it's a special type of object called an iterator. And I'll scroll down here and we'll take a look at some code involving iterators. So on line 36, I'm calling this function v.begin. The word begin here sort of has the connotation of first element, but in fact, this returns a strange object. I've named the object iter, and I would draw it on a diagram like this. I'm going to not write in a type up here, although there is a type. The auto keyword is helping me conceal a rather ugly looking type. We can view the object I create on line 36 and the return value of v.begin as a sort of conceptual pointer. I should write in this is not actually a pointer. We view it as a sort of conceptual pointer to an element of our sequence, to one of the elements of our collection. And the idea is we could use such a thing, sort of a token, a bookmark in our collection. We could use that on any collection. We could use the same concept to hold our place in a list or to hold our place in a set. It doesn't depend on things like indices or on any of the internal machinery of lists or sets. And the reason is because of encapsulation. This idea of an iterator as a sort of bookmark is an abstraction of its own, and it's encapsulated. Because what the iterator really is, deep down underneath, depends on what it's iterating over. So in this case, a vector. What it means to hold our place in the middle of a vector could be different than what it means in a list, and we don't care. The whole point of this feature is that we can use iterators that look the same way to us on a vector or a set or a list or any of the other standard collections, and that is their value. Although the notation, I admit, is not really much fun when we see it, and the reason is because it looks a lot like pointers in C. Now, the reason it looks like pointers in C is when the designers of the C++ standard library were thinking about what is a good abstraction we could use to hold our place in a collection. They're like, well, what do C programmers like? Well, C programmers love pointers, obviously, so we'll use a pointer for this. So it's important to understand the object I'm creating on line 36 isn't actually a pointer, but it's meant to behave like one. And again, you may not be the biggest fan of pointers, but they are a sort of universal C thing. C programmers can be expected to know what pointers are. So the object iter is a special object that we can use to maybe represent a bookmark in the middle of a collection somewhere. It behaves like a pointer. And you'll notice here I print out star iter. So recall from the C course that the notation star iter, we can interpret that as start at this thing, iter, and follow an arrow. And if we do that over here in our diagram, we follow the arrow and we get the number 6, because I have represented on the right-hand side the vector that I've created here on line 31 in main. So we'll try compiling and running this and see what we get. And then I want to do some experiments involving moving that iterator around inside the collection. And what we're going to notice is, of course, using iterators is generally rather tedious, and therefore we want to avoid doing it unless we have to. And these days in modern C++, we can usually avoid using iterators for almost any use other than structural modifications of our collection, or cases where we have to iterate over the collection in a more complicated way than a for each loop will allow us. All right, so I print out the vector up here with my print vector function. We saw that above. It's a pretty standard thing. It prints out 6, 8, 10, 17. At part 1, as of line 38, iter refers to, and I type star iter, and that means start iter, follow an arrow, and I get to the number 6. Okay, that shouldn't surprise us too much. And then down here, I print the vector out when I'm done. Later, I'm going to want to write this function that prints the vector in reverse to prove a different point, but we'll leave that for now. So what can I do with iterator objects? Well, I can use an iterator object to access a specific member of my collection. I can also move the iterator along in the collection. So if I want to create a new iterator over a collection, and I can have as many of them as I want, so I could have actually multiple iterator objects, each referring to a particular element of a collection at a time. If I want to create a new iterator, I typically call this function .begin. .begin returns a new iterator object positioned at the first element of the collection. In this case, of course, that's the element 6. I can then move the iterator around inside the collection using these operations. And again, these are designed to mimic the operations for a pointer. I know it's sort of odd to keep saying that iter isn't a pointer, even though it seems to imitate a pointer pretty well, but it actually isn't. It is some other type of object that is deliberately designed to imitate a pointer, apparently for ease of use, by a certain definition of ease. So when I write iter++, what I'm saying is to the iterator, adjust yourself so that you point at the next element to the right. So as of the end of line 40, my iterator will be positioned to point at the 8. At the end of line 41, after I've done the ++ operation twice, the iterator will be positioned to point at the 10. And just to prove that point, I would like to copy and paste this, and we'll just print out star iter again. There we are. And in part 2, we can see iter now refers to 10. So I can use ++ and -- to move the iterator one position to the left or right. Now, there are some clever shortcuts we can take with iterators that would allow us to, do more things depending on the collection we're working from. For this video, I really would prefer to talk about the fundamental operations that you can expect any iterator you ever encounter to have. And they are star iter follows the arrow and gets you to the specific specific element of the collection, and then iter plus plus moves the iterator one position to the right. Okay, so I could also use star iter as a way of setting an element. So we'll set this to 999. And then we'll print it out again. And what you'll notice is bits of code that work with iterators will typically start with v.begin or something similar, and then move the iterator along until it points to the element that they want. For vectors, which do support indexing, there is also the ability to move the iterator by more than one step at a time. We'll talk about that. I'm not going to talk about that in this video, though. So what I've done on line number 44, the iterator iter is still positioned to point at element number 2, but I modify it using this star notation. I modify that element to equal 999. So I've used the iterator to do that. And so hopefully we can see the iterator does represent a way of sort of holding our place in the collection. Also notice that once I've created the iterator, the operations that I do not seem to be specific to a vector. Nothing I'm doing seems to be something only vectors can do. I don't use indices. I access elements, something I expect every collection supports, and I move the iterator along. For any collection that allows me to iterate over it, well, I mean, the word iterate sort of gives it away, I should be allowed to create an iterator with .begin, and then walk the iterator along through the collection. So what I want to talk about now is how would I use iterators inside of loops? I'd like to present the use of an iterator sort of like you use an index, but again, I don't want to rely on indices because not all of my standard collections support them. So what I'd like to do is rewrite this function print vector to not use a for each loop. And so I'm going to comment this out. I'm going to steal this new line because I will want that. So, of course, this is the standard print vector function we have written over and over again in this course, but I would like to write a new version of it that uses an iterator instead. Now, to be clear, you really have no reason to write the iterator version outside of this example. The for each loop exists for a reason. It turns out that the for each loop is semantically pretty much identical to what I'm about to write. It turns out when the compiler sees something like this, the compiler generates a loop that looks a lot like what I'm going to write down here. So what I want to do is in my for loop, I could use a while loop as well, I say first auto iter, and then I set my iterator to be v.begin. And I guess I can sort of sketch that over here. If I pass in a vector, what I would do is I would begin by positioning the iterator here at the first element. So that's the iterator object returned by v.begin. I'm going to walk the iterator along until I'm done. And I don't yet know how to do that, how to know when I'm done. But at each step, I'm going to move the iterator along by one position to the right. And then to print out the element at each step, I will print star iter and then a space. So not too different than what I would do up here in this for each loop, and actually semantically looks conceptually a bit similar to the indexing loop that I would otherwise use to print a vector. The question is, how do I know when I've reached the end? So I start my iterator pointing at the first element of the sequence. At each step, I walk it along by one position to the right. And so it first hits the 6, and then the 8, and then the 999, and then I keep going, and I go here. And then I'm actually now on the last element, but we know that the loop should end at the iteration after we've hit the last element. Conceptually, we sort of want to wait until the iterator points a little bit too far past the end of the sequence. So of course, if the iterator is pointing past the end of the sequence, we definitely want to end the loop. And here is a place where the standard library designers sort of drop the ball. We're stuck with this. It's baggage now because the language already has this feature. But there's a certain asymmetry here that I really don't like, and I don't think you're going to like it either. What every collection will have, in addition to .begin, which is giving you a valid iterator to the first element of the sequence, assuming the sequence has at least one element, there will also be a special a function called .end that returns an invalid iterator, an iterator that you could think of conceptually as being positioned one past the end of the sequence. If you ever have an iterator that's equal to .end, it is invalid. So although .begin refers to the first element, .end does not refer to the last one. .end refers to an imaginary position right past the end of the collection. And that means if your iterator ends up equaling .end, your iterator has gone too far. And so as soon as an iterator equals .end, it is invalid. Iterators are designed, so we don't know how iterators work internally. We know that we can move them along one position to the right. We don't know how that works, nor do we have to. But iterators are designed so that if you move them one position to the right past the end of the sequence, so if you're on the last element and you do iter plus plus, iterators are designed so that when they get one past the end of the sequence, they will equal dot end. And therefore, you can test whether the iterator equals dot end as a way of testing whether you've reached the end of the sequence. So I'm going to write for auto iter is set to v dot begin, keep going while iter is not equal to v dot end. And we are allowed to compare iterators to each other. So the invalid iterator returned by dot end and the iterator I'm working with can be compared. I want to keep walking until iterator does equal this thing. So I keep going as long as iterator is not equal to v dot end. Okay, so we'll try that out, this new version of the print vector function. And there we go, it still prints out the vector. So the iterator I get back from v.begin, if I move it along with plus plus, it is designed to iterate over the vector in its natural ordering. So from left to right, the forwards ordering of the vector. There's also, for some standard collections, including lists and vectors, there are other alternate iterators that are provided. So for example, if I want to iterate over the collection in reverse, there is a special iterator that is provided by the vector that iterates over the collection in reverse. And this is strangely confusing because of the way, the odd, unnecessarily formal way that we have to write this. So I can also create an iterator with v.rbegin and then use v.rend. The R here stands for reverse. This is a special iterator that walks across the collection in reverse. What's weird about it is when you do plus plus, you're telling the iterator, move to the next thing in the sequence. But this iterator is designed to go in reverse, which means the next thing is actually the previous thing in the vector. I told you this was going to be tough. And the idea here is that when I iterate over a vector or a list, maybe I don't want to conceptually understand what it means to use a collection in reverse. So this rbegin and rend iterator is a normal looking iterator that happens to use an alternate order when you use it to iterate normally. Now, fortunately for you in this course in 2022, you don't need to worry so much about rbegin and rend. I'm covering them right now mostly for completeness. They do exist, they can be useful, but they are a little bit of a headache because it's odd that we have this special alternate iterator that when you walk forwards, it walks backwards. But it does exist. And the point that I want to prove is once I have the iterator object, I just use it. I don't worry about what's going on behind the scenes. I don't worry about how exactly it's navigating internally inside the collection. I just care that it is. All right, so we'll try that and we'll verify that we can print out the sequence in reverse. And there it is. The sequence has been printed in reverse. Okay, so a few questions. One, why do we need iterators? Well, okay, we'll ignore the reverse iterator situation for now. Why do we need iterators at all? This just the standard iterator, why is it useful? Okay, so one reason is we might work with collections that don't have any obvious way of referring to one specific element, like we do with vectors, where we use indices. Another reason is there are operations that are common to all collections, like insert an element at an arbitrary location. Operations like that. And those operations, because they're common to all collections, use a common syntax, a common notation. And because the way that all collections together refer to individual elements is with iterators, even if you want to insert at an arbitrary location in a vector or remove from an arbitrary location in a vector, you have to use an iterator because that's the convention used by all standard collections. The next video will talk a bit about that, still in the context of vectors, but the types of operations you would use to do arbitrary insertion and removal in sequence collections like list and vector.